Hi, my name is Pat Helland, and I'd like to talk to you about some thoughts I have about coordination. The title of this talk is I'm So Glad I'm Uncoordinated, and the subtitle is Coordination is Increasingly Painful. What can be done? Now, these are my own ideas and opinions. They are not necessarily reflective of the positions of any of my employers, past or present, and I'm currently employed at Salesforce. I am an uncoordinated person. I drop things. I can't catch moving objects. When I was a child, I was told to go play baseball with everyone, but Little League was awful. I couldn't stop that moving ball, and it was just scary out there, so I quit after 1 week. I started reading books and not playing sports, and on a whole, that worked out well for me. So let's talk about the agenda for today's talk. How things have changed is the first section. I started getting paid to develop software in the 1970s, and now here it is in the 2020s, and things have seriously changed. Then I want to talk about the partial collapse of partial order. It's an abstraction for how to think about what coordination is. Then, what is coordination? How can we go Zen on it? How can we kind of work with it to minimize the impact of it? And finally, talking about coordination in a stretched out world. Things have definitely changed since the 1970s, when I got my first programming job, until now in the 2020s. Let's look at that. So, latching in my first programming job. In 1978, I got my first programming job. It was on a little mini computer called a BTI 8000, which was a symmetric multiprocessor, meaning you had lots of CPUs sharing the same memory. And furthermore, it was a shared backplane, and you could plug the CPU cards in. And at the time, we just didn't talk on the network. It was not a common thing. This was scalable computing. You could plug in more CPUs, and it turned out that with 7 CPUs, you got 5.5 times as much throughput, and that was really special at the time. It had a 15 megahertz clock. And furthermore, to get to memory took 12 cycles, or 750 nanoseconds, to read or write memory. Now, the memory was coherent because the CPUs didn't have caches, and so you got the latest value out of memory. And latches, to protect shared memory, reads and writes each took 750 nanoseconds. And so at that time, it was really cheap to coordinate because a latch took the same cost as a read or a write. But boy, CPU was expensive and we were optimizing it. Memory was expensive. Storage was expensive. Bandwidth was infinitely expensive because we didn't have any. Now, over time, we are getting more and more stuff. With Moore's law, the transistors double every 18 to 24 months. So more CPU, more SSDs, more NVRAM, more DRAM. And now we've gotten to the point where there are 50 billion with a B transistors per chip, and it continues to go up. It's fascinating to see these changes. Similarly, if you pay attention to Gilder's law, the total bandwidth triples every year. We get more connections, we get faster connections, and nowadays in the data center, you're seeing 400 gigabit Ethernet now and 1 terabit Ethernet very, very soon. It just keeps on going. Now, in 2004, Dave Patterson wrote a really cool paper called Latency Lags Bandwidth in the Communications of the ACM. And he observed that as time goes by, and this is an exponential log chart, so you can see the big difference, that the capacity of these things, microprocessor, memory, disk, and network, goes up a lot faster than the time to get to them shortens. And these are statistics from 1982 to 2004, but this trend is still true 18 years later. And one of the observations is that while the latency improved about 10x during the period of time from 82 to 2004, the bandwidth, the capacity of each of these was either 100 times or 1,000 times as big of an improvement. And he says bandwidth improves by at least the square of the improvements in latency. So it's getting much easier to get bandwidth than to get latency. Why does latency lag bandwidth? Well, there's an old network saying, bandwidth problems can be cured with money. Latency problems are harder because the speed of light is fixed and you can't bribe God. I strongly recommend anybody go back and read the 2004 paper by Dave Patterson. Very interesting and still happening today. So we wait for stuff that's far away. When we compute, the CPU core needs data. If they don't have it, they wait. The farther away the data, the longer the CPU core waits, and waiting is inefficient. So if I have a register that's actually on the core that's close to the CPU, it's about 10 microns in physical distance and, one cycle, 0.3 nanoseconds to get to. Now, each of these cores typically has an L1 cache. It's about a millimeter away or about a nanosecond to do round trip. The L2 cache, which is shared across the cores, is typically about 5 millimeters away and 6 nanoseconds round trip to read and write. If you have multiple sockets, then you might have an L3 cache, which is about 50 millimeters away or 25 nanoseconds round trip. Now, once you get off of that and try to get into DRAM, that's about 2 centimeters or so distant. It varies, but 100 nanoseconds round trip is a pretty good rule of thumb. Now, heaven forbid you're going to go do an RPC to another server in the same data center. That'll take you about 150 microseconds. It's about, 100 meters maybe round trip to get in the same actual physical building. If you're going to a different building, like a cross availability zone, that might be 2 kilometers or a millisecond round trip. Now, heaven forbid you're going across region, you're going, 2,000 kilometers away for disaster protection. That might be 200 milliseconds round trip. It's a long distance. I want to point out that going to another server in the same availability zone is 3 million times as long as getting something off of the register in the actual core itself. And it's 600 million times as long if you want to go across a distance to get to a different data center. So let's put latency in perspective in the 2020s, in 2022 to be precise. This slide is motivated by a table that is in a paper called AlphaSort, a cache-sensitive parallel external sort for VLDB, written for VLDB in October of 1995. It's a great paper. It talks about the computer perspective of how long it takes to get stuff versus the human perspective of how long it takes to get stuff, just as a ratio, just to make it just hit home the difference. So we're going to talk about distance. We're going to talk about latency in wall clock time and latency in cycles. And then the instruction opportunities that you have or are missing as you wait for something. We're going to put a ratio on that and compare it to things in our human life, just to talk about the ratios. So in a CPU register, that's 0.3 nanoseconds at a 3 gigahertz clock. That's one cycle, or 5 or so instruction opportunities on modern computers. Call that a ratio of 1. And let's start and say, I'm going to get something out of my pocket in my shirt, and that takes me 1 second. An L1 cache is per core. And that is 1 to 1.2 nanoseconds time to get from the per core cache. 3 to 4 cycles, or 15 to 20 instruction opportunities if everything's great. 4 times as far as a register inside the core. And if it's 1 second to get it from my pocket, it's 3 to 4 seconds, or I could get it from my desk at work. An L2 cache, that's the same core. It's multi-core, but the same socket. It's across cores. That's 6 nanoseconds in wall clock time, or about 20 cycles to get. That means I've got about 100 instruction opportunities at 5 per cycle. That's a ratio of 20 to 1 compared to the CPU register. So if it's 1 second from my pocket, it's 20 seconds to go get it. That's kind of like going to a file cabinet in my office. L3 cache, that's cross-socket. That's when you've got multiple sockets with different cores. And so that would be 24 to 30 nanoseconds, 72 to 90 cycles. And during that period of time, I would lose 400 to 500 instructions that I could have done while I'm waiting. That's an 80 to 1 ratio from the CPU register. Or if it's 1 second from my pocket, it's about 80 seconds or about a minute and a half. And that's kind of like climbing the stairwell to go see someone on another floor at work. DRAM, that's 80 to 100 nanoseconds, or 260 to 330 cycles. Call it 1,000 to 1,500 instructions, or a 300 to 1 ratio against that register inside the CPU itself. So if it's 1 second to get to my pocket, then it's 300 seconds or 5 minutes. I could walk 2 city blocks during that period of time. So suppose I'm going across server with an RPC over TCP, and that's inside the same availability zone. That's maybe 150 microseconds, or maybe 450,000 cycles, or 2 million instructions, and that's 450,000 times as far as getting it off of a register in the same core. So again, if it's 1 second from my pocket, it's about 5 days in time, and some healthy person could maybe walk 100 to 150 miles in that 5 days. Finally, if I'm going across availability zones, that's about a millisecond, or about 1 million nanoseconds. That's 3 million cycles. And I've lost about 15 million instruction opportunities while I waited for that RPC to go over there and come back across availability zones. About a 3 million to 1 ratio compared to the register in my core. So if it's 1 second to get something out of my pocket, it's pretty much a month to go and get something out of, this distance. And I could maybe walk, or someone healthy could maybe walk 600 to 900 miles during that month. But even more, there were some really interesting things to think about in comparing that paper from 1995 to what we see today. In 1995, the CPU clock was 150 megahertz, and now it is 3 gigahertz. But getting memory from DRAM, getting data from DRAM, at the time took 80 to 100 nanoseconds, and today it still takes 80 to 100 nanoseconds. Reading and writing DRAM does not get faster as time goes on. So then it took 12 to 15 cycles because the cycles were longer. Now it's 260 to 330 cycles. What that means is DRAM is 21 times farther away now than it was in 1995 in terms of instruction opportunities. But it's even worse than that, because now we're getting closer to 5 instruction opportunities instead of 2 then. So it's kind of sort of closer to 50 times as far away today as it was in 1995. So Hubble's universe, everything is getting farther away. There is more and more thinking going on while you wait. Now we can store more stuff. We can move more data per millisecond. We can think more per millisecond. But there's more thinking while waiting for stuff. And the farther away the stuff is, the more painful it is. So I tend to think of that as Hubble's expanding universe, where as time goes on, everything is getting farther away from everything else, just as DRAM is farther away now compared to what it was in 1995. Waiting. We wait to read, we wait to write, we wait to coordinate. So if we wait to read data from far away, how do we deal with it? Well, mostly we try to deal with immutable data that's easy to cache. We know it means what it means. But we now get a lot more per round trip. Where we used to take a little tiny scooter load, now we go and get a massive freighter full of data and bring it across because we can get it in roughly the same amount of time. But what about waiting to write data that's kept far away? Well, the trick we kind of use that helps a bit with that is we append writing to a log, and we can batch the appends. So lots of things can be written in one round trip. Now, because it's a log, that's a little harder to read, and so we're constantly reorganizing that log, and that's where you see log structured merge systems and things like that, as we reorganize that data that we wrote into a log. But waiting for coordinate. What is coordination? Parallel activity is important for many, many things. When can distant activities remain parallel? When do those parallel activities need coordination? Well, I argue coordinating is actually aligning parallel work. Parallel activity is really powerful. It can be concurrent threads, concurrent servers, concurrent work, different data centers. All of these things are very powerful doing parallel stuff. And coordination is aligning parallel work. We want to share data. We want to know when steps have been completed. We want to advance to the next step in a workflow. So we're aligning that parallel work. Now, coordination in 1978, when I first started programming, we had multiple threads and multiple CPUs, and we were latching that shared data so that we wouldn't make a mess when we were, two different threads were trying to work on that same data. So you would, get the latch. And then when you got the latch, you could modify the shared data, and then you would release the latch. And now another thread could get the latch and again modify the shared data and again release the latch. Coordination in 1978. If you didn't fight over the latch, if you got it right away, it took the same time as a single instruction, which was a single read and a single write. So the latch was the same time as those in 1978. Coordination in 2022 is a lot more complex. You have multi-core latches, and so they're in different cache lines, and you may have to get them close, you may have to get them far away. And also you might coordinate by using Zookeeper via RPCs. Well, each RPC takes a long time, and if you use Zookeeper, you talk to the leader, and then it talks to a bunch of followers, and that takes a long time. And then if you try to talk to a database via RPCs, that takes a really long time. So in 2022, there are varying coordination delays. In the same server, the cache line might be close and 1 cycle away, or it might be far away and it's like 300 cycles. If you have a remote server RPC, that, if you're lucky, is only 450,000 instructions you've waited, and it might be 3 million. And that's uncontested coordination. That's not even a database. That's not even Zookeeper. It's much worse if you fight for access, and it's much worse if you use these sophisticated mechanisms to coordinate in a distributed system. Lots of thinking is now not happening while you wait. So how things have changed. In 1978, coordination was cheap, same cost as a read or write, but CPU, memory, storage, and bandwidth were very expensive. Now, CPU, memory, storage, and bandwidth are very cheap and getting cheaper every couple of years, but it's expensive and increasingly expensive to coordinate. Is there an abstraction for coordination? What can we do to reduce the pain? Now let's talk about the partial collapse of partial order, an abstraction for coordination. How can we think of history in a system? There are lists, there are trees, and there are DAGs. In a list, one thing follows exactly one other thing. Everything has one parent, and each parent has one child. In a tree, you can have many things following one thing. Each has exactly one parent, each parent may have many children. Now, in a DAG, or a directed acyclic graph, each thing may have many parents and many children. You don't have cycles in history because you can't be your own grandfather, so we don't have cyclic graphs in the history of a system. Leslie Lamport defined the ordering of events in a distributed system. He said there are multiple processes. Each of them can send and receive events, and events or messages define the system order. Here we see process P, process Q, and process R. Now, happened before is the ordering of events. The stuff at a sending server happened before it sent the message, and that includes the happened before of a sender when you receive a message. So you have this partial order. And the messages form the partial order, which is a DAG, or directed acyclic graph, of processes and events. Your time is after all that happened before. Let's do an example. If I have process P that does an RPC to process Q, it has a time, and then the time the message is received is a little later. Process Q does its stuff. A little later, it sends an answer. Now, process P's time is after the response was sent from process Q. So what is a total order? In a total order, one thing happens one after another. Each thing has one predecessor. Everything is either before or after what you do. In Newton's universe, time marches forward uniformly. All clocks are the same, and time moves forward one step at a time everywhere at the same pace. In von Neumann computing, one instruction follows another. In that central computer, all clocks are the same clock. Now, Einstein and Lamport pretty much talk about time as a partial order. In a partial order, everything is before something else, or after something else, or side by side with something else. Partial order is a directed acyclic graph. Things may follow many predecessors, and many things may follow you. For Einstein, each thing had its own clock. They follow all their predecessors, but the clocks may be slow relative to other clocks. Paths through the universe may see a different duration. In Lamport, your predecessors happened before. You follow all of your predecessors. Clocks may be slow relative to other clocks, and paths through the network may see different durations. If we zoom in on one thing inside of that massive directed acyclic graph, subjectively, I really am the center of the universe. The partial order is a directed acyclic graph. Each piece of that directed acyclic graph stands in isolation, messages coming in, messages going out, living in its own time. With Lamport clocks, you're after what happened before. I see what happened before me. I don't see what happened after me, and I don't see what's happening elsewhere. So, how can I reunite branches of that partial order? Coordination is the act of reuniting those branches that exist in a partial order. They may be far away, they may be close by. They may be far away in space, or they may be far away in time. Here we see 4 different branches coming into one thing, and only after those 4 have aligned can you move ahead. And here's another case where 2 things are coming together. And bringing together those branches of the partial order is what I believe characterizes coordination. Now, aligning multiple inputs can be painful. Aligning in time is hard, and aligning distant servers in space is hard. The partial collapse of partial order. Our universe is a big place. Our Earth is a small part of it. The computation on Earth is a subset of the universe. A partial order is smaller than the universe's total order. Stuff in Andromeda is sharded from stuff on Earth. Coordination can be small or it can be large. It can be across threads, it can be across cores, it can be across servers, departments, or companies. And coordination is actually kind of fractal. The closer you look, the more coordination you see, and it occurs at all of these dimensions. So coordination is the partial collapse of partial order, and coordination reduces the disorder within a system. Going Zen on coordination. How can we relax and use some tricks so we don't have to coordinate so much? Let's talk about some ways to relax coordination. Let's break them into 5 different categories. First, space, then time, then layers, equivalence, and finally confluence, that property of some programs where the natural order that exists in your computation, meaning the execution of it can be in many different ways and doesn't have to be coordinated and give you the answers you want. First, let's talk about space. So we can relax coordination with space. If I have a different space, I have separate coordination. This can be very big. Earth is separated from the Andromeda galaxy. It can be very small, where I have a thread private buffer in a shared memory system. What is separated by space? How do I use it? Well, if I have memory that's separated in space, I can do reads and writes to memory and they don't get tangled up, and that's all good. I can have objects that are separated in space, and I can view them from the outside by interleaving the client requests. And the best paper around this is Herlihy and Wing's paper on linearizability. It describes an object, a centralized single object, and clients in different locations, and they send a request, the operation gets performed on the object, and then a response comes back to the client. And the paper formalizes the timing of the request and the response to the object. And I'd like people to notice the object is not necessarily, the operation is not necessarily reads and writes. It can be arbitrary things. Also, you can have a serializable database, and Kinda, if you squint and pretend it looks linearizable from the outside, one thing happens at a time. One transaction appears to happen one at a time in a serialized database. Now inside there's lots of things happening in parallel, and the database itself keeps them from getting tangled up. So it looks linearizable from the outside, but parallel on the inside. And that's one way of thinking about space. It can be memory, it can be objects, it can be a database. Things are separated as they're executed. And now let's talk about time. We can relax coordination with time. Fate sharing is one technique to relax coordination. If I do a second operation and it only happens if the first one commits, I can tie them together and reduce coordination by managing the fate sharing of the second based upon the first and the third based on the second. I have dependencies on earlier stuff. Speculation is a way to defer coordination until a bunch of things are done, and then only at the end decide if it should all happen or not, if it should all stick or not, so you don't coordinate as often. Immutable data is a technique to coalesce speculation. If I have immutable inputs, they are the same by definition, and I can apply then functional programming, which will always give me the same answer out of that same input. Very powerful technique we use to relax coordination quite commonly. With pre-allocation, we speculatively get more stuff. So if it's expensive to get the stuff, let's go get a bunch of it, and we'll keep it on hand, and then we can give it out in a smaller grain and avoid the waiting for that. And so pre-allocation is a form of speculation that gets stuff in advance. Retries after timeouts, that's similar to speculation. I'm taking idempotent work I can do over and over, and I retry it in order to bound the latency. The first attempt didn't answer quickly, so I try it again over here, and then that answer happens more rapidly, and I can bound that latency. That relaxes coordination. Now let's look at how layers can help relax coordination. Layers of abstraction allow you to avoid side effects across the layers. If I have a higher level operation, I can reduce the coordination that's needed. This happens because I can avoid false dependencies. Early on, when people built database systems, they used page locking with many records in the same page, but they locked up the page with all of those records. Sometimes that meant that other people waiting for just different records had to get stuck behind the page itself. That was a false dependency. Databases have gone to finer grain abstractions, not about pages, but about records. Similarly, you can have microservices that encapsulate their memory. I don't need to worry about how memory is managed inside of a microservice or many details of that because I don't have those false dependencies when I view it from the outside. I can avoid interference by coordinating externally visible semantics and not the internal details, and that can relax the coordination. Similarly, commutative operations, or the kind of interfaces, the kind of high-level work I'm doing, can help to isolate partial order and avoid coordination under many circumstances. This is the crux behind CRDTs, or conflict-free replicated data types, that allow reordering by having equivalent operations as you do the work. Now, this is very similar to the next section on equivalence. Let's look at how equivalence can help relax coordination. With equivalence, good enough is good enough. I don't want to sweat the details. One example, if I have a whole bunch of caches, a whole bunch of replicas of a cache with lots of readers, but in the background I'm updating those replicas as changes have happened to the data I'm caching, sometimes I'll read a new version, sometimes an old one, but if I don't care, I don't care. And so that being equivalent, being good enough, allows me to relax the consistency and avoid coordination because they're both just fine. Equivalence means it looks the same to me, whatever the heck that means. So a dollar bill is a dollar bill. It can buy a certain amount of stuff. But if you're giving your grandkid a $100 bill or something for their big birthday or big celebration, you want to get a nice, clean, pretty one from the bank, not an old beaten up one, even though they both buy the same thing. So here, the equivalence is the purchasing value of $1. A bushel of wheat is an equivalent collection and weight of wheat with certain standards. King-size non-smoking rooms, well, they're king-size, they're non-smoking, and one should be as good as the other. And you have to ignore the differences. Room 301 might be next to the elevator and be very, very noisy, but it is still a king-size non-smoking room, and so we ignore the differences. There is a duality in this approach. It is private. I want a king-size non-smoking room when I make my reservation, but the pool of them at a particular hotel is shared. And when I ask for one, I might get told, nope, we're all full because you booked a reservation and then you canceled it. And if I had waited a day, I might have gotten that room. So the private work allocates one of the individual things, but the shared pool must manage the capacity. And that is a deferred coordination because usually the pool is not running out, but there is some coordination that actually spans these equivalent operations. Now let's talk about confluence. Confluence, the ability to do any order of execution and get the same output as a property of some programs. We can relax coordination with confluence. Confluence is defined as a property of programs. Not all programs have it, but a property of programs where the same inputs will always give the same outputs, even if you bust it into a number of pieces and you execute the pieces in different orders. The different orders of execution doesn't affect the output. And you see in the picture up here, there's different orders of B, D, A, C on the left, but as they execute and work their way through the computation, it comes out in the natural order of A, B, C, D. Confluence requires some natural order. The output must have that natural order, and that means the different executions can give you that same answer. Massively parallel work leverages confluences quite often. It's the standard trick. You break into pieces, order across the pieces doesn't matter, you execute them in any order. You can defer the coordination across the pieces. An example of this is MapReduce. The key in the map actually allows you to independently execute the different pieces of the work. Similarly, sort has a predefined answer of the correct answer based upon the natural sort order, and so you can break it into pieces and make it work. SQL has many set operations. The individual computation to accomplish the set operation can be busted up differently, but the answer is consistent in the same. And these are examples of confluence, a powerful trick for reducing and relaxing coordination. So we've seen space and time and layers and equivalence and confluence. These are just the ways I've imagined. There may be more. I'd love to hear from you if you have more, but these are some of the ways of thinking about how we relax coordination. What is coordination in a stretched out world? How can we apply these tricks to make things easier and better? So let's look at some examples. The first example is a per thread memory pool. Suppose you have a bunch of threads, maybe a bunch of processors sharing memory, and they contend for a shared pool, but that latching, that fighting over permission to get at the memory pool is getting too painful. So what do? You make multiple pools, one for each thread, and you go and you grab stuff out of the big memory and you give it to a little pool so that as the thread needs little pieces of memory, it can get it out of its local pool until it runs out and you have to go back and get more. That is an example of using 4 of the 5 techniques I've described. It uses space with buffers. It uses time with pre-allocation. It uses layering by that abstraction of get me memory, I don't care where, but malloc, I want to get some memory. And it uses equivalence by saying, oh, the pointer I get back, I don't really care if it's in a shared pool or a per thread pool. Now we see the next example is massive replication of caches with asynchronous updates. What do I mean? One example, I'm doing e-commerce. I have product descriptions and a bunch of batch jobs in the background that are figuring out the way the product description for this product and that product have changed. They're pushing them into caches that are being read as you shop. Now, the caches typically have many replicas. So when the updated product description hits one replica, it's not in the other. So depending upon which replica I hit, I get the old or the new one, but it doesn't really matter. They're equivalent. Similarly, if I'm doing searches of the web or something like that, all these documents are being fed in. They're being sorted based upon the n-grams or the sequence of terms that I might search on, and then those are being pushed out into their shards, which have a bunch of different documents per shard, and you're looking for documents that match the pattern. So those updates happen from batch jobs. You can read any replica and retry, but the answers are varied when retried. Similarly, these use the same 4 tricks. Space with shards and items, time because I'm retrying for latency, layer because the items in the cache are they have an interface that describes get me the item, and equivalence because the staleness is okay. The next example is we want to reduce the time it takes for a CPU core to get memory from another cache, from a different cache into its processor, or from DRAM into its processor. So the trick is you speculatively predict the instruction branches. Every time an instruction says I could go left or right, you actually try both, and you continue to look down all of those possible paths through the CPU instructions to touch anything I might need and pull it into the core before I need it, hopefully. Now, an example of this is the Apple M1 chip is very interesting, and it has 600 to 800 out-of-order executions per core, and there's typically like 10 cores in this chip, and it's really marching ahead and trying all of these possibilities. And since it's only executing 6 or 8 per cycle, that means literally 99% of the instructions that it executes are for naught, other than the fact that it allowed it to earlier touch and predict when the cache line is needed and go pull it close so you don't have to wait so long to see that. This uses 2 of the 5 tricks. It uses time via speculation, and it uses layer via caching versus execution. The CPU instructions don't even really think about the data and where it's located in DRAM or cache. They're just executing, and then the cache layer has to manage pulling that data close. The next trick is a record-oriented relational database, the next usage of these tricks, rather. Record locking for transactions and page locking to control the internal buffers happen all the time. You cache data inside the database from whatever its external storage is. There are set-oriented operations that can be executed in many different orders and yet give a predictable answer. And you're frequently allocating big blocks of memory in this shared system from the shared memory and then using them per thread. So here we see all 5 of the tricks we discussed being leveraged to implement these complex relational database systems. You use space with record and page locking, you use time with pre-caching of data, you use layering with records and blocks and many aspects of layering. There's equivalence of memory allocation and many other times, and confluence with the set operations to give you those set-oriented relational answers you're asking for. If I have an internet search operation, what am I doing there? Well, you put some terms in, and they get turned into these n-grams, which is one word or a sequence of words that you want to look for in a document to see which documents have this and this and this. You shoot those terms out to a bunch of shards with a bunch of documents that can then tell you which documents have those terms. And then you look for the ones that have the terms that you really need across those shards. If one of the shards is too slow, then you retry to another replica of that same shard that's described in this wonderful paper called Tail at Scale. But it turns out you don't care if that's the same replica has been updated and this one hasn't. They're both great. They're equivalent. They're pretty good results. And then you intersect those documents looking for the documents that have all of the search terms you want, and that is a set-oriented operation which can be broken down into confluent processing. Again, this very sophisticated system uses all of the 5 types of tricks that I've described to reduce coordination. It uses space with shards, it uses time with retries to replicas, it uses layering in the interfaces to the shards, it uses equivalence of the contents as they're being updated in the background, and this version's as good as that version, and it uses confluence to do the set-oriented operations to describe which of the documents to keep out of the ones that have the various n-grams within them. Last example is a transactional database using optimistic updates. What is this? That's where the application reads the database and then plans the updates it hopes to make in a transaction. And then it reduces the trips to the database by bundling many updates into one trip and saying, if I can do all of these things and all of the stuff I read matches what I saw, then I want to push that back. And only if there's no collisions to other changes are those updates committed. But it allows you to reduce the round trips to the database and is a hugely important trick that we use. Now, this uses two basic aspects of these relaxation tricks. Space, by separating the application from the database so they can live in their own little world until you try to commit, and then time, where you're batching up the changes. So it's yet another example of relaxing these tricks using different categories. It is expensive to decrease disorder. So paraphrasing the second law of thermodynamics, disorder in the universe continues to increase. It goes on and on, getting more and more complex. It takes energy to reduce that disorder. If I want less disorder over here, that takes energy from over there to cause the disorder to be reduced here. It is easy to break an egg. You start from the ordered egg and you end up in the disordered broken egg. It is very hard to take a disordered broken egg and turn it back into that original egg. Coordination is also hard. It takes energy to decrease the parallelism in a system. Aligning parallelism incurs costs throughout the system to do that. It is easy to increase parallelism. It is hard to decrease parallelism. It is hard to coordinate. So don't coordinate when you can avoid it. So what are the takeaways I hope you remember from this presentation? It used to be that coordination was very cheap. It cost the same as a read or write to memory. But at that time, CPU, memory, storage, and bandwidth were very expensive, and we were working hard to optimize them. Nowadays, CPU, memory, storage, and bandwidth are cheap and getting cheaper, and every few years you get more. But what's more painful is coordination. It loses you opportunities to do work, and that loss is getting more and more challenging as the years go by. So computing has changed and is still changing. So our solutions are changing. When we read, we go and get a lot of immutable data and bring back lots at once. When we write using logging and batching updates to the log. And then because they're all not organized properly, then later we reorganize them with log-structured systems, such as log-structured merge systems. When we coordinate, it's very hard to pick an authority, and it's very hard to find out the latest truth. Things that are not the latest are relatively easy, but coordinating the latest is pretty darn hard and getting harder. What is coordination? I argue coordination is the partial collapse of partial order. Where there was parallelism, we're reducing that parallelism, and that is what I think is coordination. In happened before, we have a partial order in a distributed system with parallel execution. Coordination is where we're combining that parallel stuff so it executes together, and we bring it together as we collapse that partial order. We need to coordinate less often. Keep stuff isolated in some dimension or multiple dimensions. And we see that in space with shards, buffers, threads, companies, data centers, keeping at distance and space. In time, with speculation and retries and optimistic concurrency control, there are a set of tricks related to time. We can reduce coordination with layering by focusing on fine-grained records versus blocks, minimizing internal details and masking them. Microservices encapsulate things, modules encapsulate things. We can use equivalence with king-size rooms and malloc of memory where we don't really know what the pointer points to, but we got the memory we need, or bushels of wheat. And finally, we can use confluence, where we leverage an existing order, and the execution of the pieces doesn't need to be coordinated. They can be disordered, and then you pull it all together when you're all done. I am so glad I'm uncoordinated. It's important to avoid or reduce coordination when possible, and to think about the tricks to minimize the pain. For me in my personal life, being uncoordinated has advantages. My wife never lets me fix anything around the house because it's cheaper to call a repair person before my involvement makes it worse. Consequently, I can read and write and work on presentations like this. So in our agenda, we saw how things have changed from the 1970s to the 2020s. We talked about an abstraction that I like to talk about as the partial collapse of partial order. We tried to go zen on coordination by talking about tricks that allow us to avoid it. And then we looked at ways we can combine those tricks in the real world solutions we see today. So avoid coordination whenever possible. Works for me. So in our agenda, we saw how things have changed from the 1970s to the 2020s. We talked about an abstraction that I like to talk about as the partial collapse of partial order. We tried to go zen on coordination by talking about tricks that allow us to avoid it. And then we looked at ways we can combine those tricks in the real world solutions we see today.